a very simple problem that has to do with matrix multiplication. So suppose that I have two matrices and I want to multiply them. So let's say I have one matrix A, which is n by m, and then I want to multiply this by another matrix B, which is m by t, let's say. Right? So what is the cost of doing this kind of multiplication? Let's imagine that I'm not doing anything smart. I'm not using things like Strassen or so on. So I would just calculate every entry of the result. So let's say the result is C, and of course the result is going to be an n by t matrix. And then as we've seen before, Cij is just going to be the sum of Aik times Bkj for every k, right? And if I just use this formula to calculate my matrix C, then the cost would be n times m times t, right? So the number of multiplications that I'm doing, or the number of operations that I'm doing, is basically n times m times t. Okay. Now imagine that I have a chain of matrices instead of just two matrices. Let's say I have many different matrices and I want to multiply them. So for example, let's say I have a matrix A, and this matrix is 10 by 100. And then I want to multiply this by another matrix B, and this is 100 by 5. And then I want to multiply this by another matrix C, and this is, let's say, 5 by 10. Okay. So the result would be a 10 by 10 matrix. But I can do the multiplication in many different orders, right? So I can first multiply A and B, and then multiply the result by C. Or I can first multiply B and C, and then use that, multiply A by the result, right? Now the result is going to be the same anyway, no matter which one of these two orders are used. And actually in this case, I only have two orders, but you can imagine if I had more matrices, I would have many more orders. But the cost is not the same. So sometimes I would have a smaller cost, sometimes I. For example, what is the cost here? If I first multiply A by B, so the cost is 10 times 100 times 5, right? 10 times 100 times 5. That's the cost of the first multiplication. And then I get this matrix here. And what is the size of this matrix? This is a 10 by 5 matrix, right? And then I'm multiplying it by C, which is a 5 by 10 matrix. So the cost of the second multiplication is just going to be 10 times 5 times 10. Okay. So this is basically, well, this is 5,000, and this is 500, so 5,500 overall. Okay. Now let's say I do it in this order. I first multiply B by C. What is the cost in this case? So times 5 times 10. That's the cost of multiplying B by C. And then plus, well, I get this matrix here. And because my B was 100 by 5 and C was 5 by 10, B times C is 100 by 10. Right? It would have been better if I just used commas here. So let's say this is a comma, this is whatever. Okay, too late. So if I multiply A by that, I'm multiplying a matrix which is 10 by 100 by another matrix which is 100 by 10. So the cost is 10 times 100 times 10. And now you can see that this one is, again, 5,000. But this one is 10,000. So my total cost is 15,000. I'm really bad at doing multiplications and sums, so I hope I did that correctly. So anyway, the point is that the order matters. If I multiply my matrices in different orders, they're going to have different costs, and my runtime would be different. So if I give you a chain of, let's say, 1 million matrices, and I say I want to multiply all of them together, it makes sense to first find the best multiplication order, and after you find the best multiplication order, then go ahead and apply it, right? So the problem that we want to focus on is finding the best multiplication order. So this is our problem. I'm going to call it chain matrix multiplication. And the input is just going to give you the sizes of matrices. So imagine that I'm multiplying n different matrices. Each one of them is going to have a number of rows and a number of columns. Okay, so I have a bunch of matrices A, let's say, I don't know, A1 times A2, so on to AN. I want to multiply all of them. But I'm not going to give you the matrices themselves as part of the input. I'm just going to give you the sizes of these matrices. So let's say that my matrix AI is like this. So I'm going to say my matrix AI has Ri rows and Ci columns. So my input is not going to be actually the matrices. It's just going to be 2n numbers, the Ris and Cis, the number of rows and columns of every matrix. Okay, and then as the output, I want you to write the cost, the optimal cost of multiplying all of these matrices together. So the cost of multiplication, but of course I want you to optimizing, so using the best possible order. Okay. Just as before, I could also ask for the best possible order of multiplication itself. That's just tracing your steps in the dynamic programming. So I'm not going to focus on how to find the solution itself. I'm just going to tell you how to find the cost. Okay. So the dynamic programming that we're going to do is actually very similar to what we saw in the previous session. I'm going to say, suppose that I want to multiply AI plus 1 to AJ. What is the minimum cost to do this? And I'm going to save that as a subproblem. So I'm going to have a subproblem. Let's call it ans IJ. And this is going to be the minimum cost for calculating AI times AI plus 1, so on to AJ. So instead of saying I'm multiplying all of my matrices together, I'm saying I'm starting from the ICE matrix and I'm multiplying only up to the JS matrix. And the question is, what is the smallest cost if I can only have these matrices? And then, of course, my final answer would just be ans 1n, right? Because that's the minimum cost of multiplying everything. But now, again, the question is, how do you actually calculate this? So I have this from index I to index j, and I want to multiply them together. Now, in this case, it's quite easy to talk about base cases, right? If I is equal to j, if I have only one matrix, my cost is 0. Because I don't have to do anything, I just have it, right? So I say if I is equal to j, ans ij is just 0 because there's no multiplication to be done. But otherwise, I have these matrices and I have to basically make a choice. I have to decide which multiplication I want to do first, right? But that's not a good casework. If I want to do a casework on which multiplication I do first, that first multiplication is actually going to change my matrices, right? So if I say I take matrix number 5 and 6 and I multiply them together, that's great, but it doesn't give me a sub-problem because matrices 5 and 6 become one matrix now, right? So I don't like to do that kind of casework. I don't want to say that if I want to multiply all the matrices from index I to index j, let's figure out which multiplication to do first. But I can do the opposite. I can say which multiplication am I going to do last? Okay. So again, this is my situation. Let's do just an example. Let's say I want to multiply A5, A6, A7, A8, and A9, right? I have to do one of these multiplications last. Let's say that I decide that the last one is going to be this one. If this is the last multiplication, then I have to first find the result of the left-hand side, then find the result of the right-hand side, and then multiply them, right? But I can use a sub-problem to find the result of the left-hand side. That's just the answer for 5, 6. And I have another sub-problem, the answer from 7 to 9, which tells me what is the cost of finding this one. Finally, I have to know what is the cost of this last multiplication. But that's also quite easy to find, right? What is the cost of this last multiplication? You just have to figure out what is the size of this left matrix and what is the size of the right matrix, right? But the size of the left matrix is that you read the number of rows from the first matrix, the number of columns from the last one. And the same thing here. You read the number of rows from the first one, the number of columns from the last one. Okay. So based on this idea, I'm going to write my recurrence relation. I'm going to say if I is not equal to j, so let me move this down. If I is not equal to j, let's figure out which multiplication is the last one. Okay. So I'm going to say for every k, okay, initially I'm going to just say my answer is infinite. Okay. And then I say for every k from I to j minus 1. So this is the casework, and I'm considering the case when the last multiplication is between k and k plus 1. Okay, when ak, whatever before it, times ak plus 1 and everything after it is the last multiplication. Okay, now what would be the cost here? The cost, let's call it C, would be the cost of finding this first part. So that's just the answer from I to k, plus the cost of finding this second part, which is just the answer from k plus 1 to j, right? Plus the cost of this last multiplication. But the cost of this last multiplication is, again, just based on the number of rows and columns in each side. So how many rows do I have? I have as many rows as the first matrix here. So that would be C sub I, sorry, R sub I, the number of rows. And then the number of columns is the number of columns of the last matrix here. So that's C sub k. I just realized I shouldn't say C here. Maybe let's call it cost. And then I also need the number of columns of this last one. So C sub j. Right. Hopefully I did this correctly. Again, I'm not really good at doing these things correctly, but that's the cost of the last multiplication. That's what you have to understand. Okay. So, and then my answer just becomes the minimum and the current cost. That's it. So basically, I'm looking at all of these cases. I'm saying k can range from I to j minus 1. Take the cost for each of these cases, and then take the minimum of all of them. And that's going to be my answer. Sorry, I forgot to put the ij there. So ans ij is going to be the minimum of ans ij and this cost. Okay. So this is my dynamic programming. And again, here I'm not really talking about the order in which I'm going over my subproblems. I'm just saying for every subproblem, how I can find the recurrence relation. Okay. What is the ordering that I have to look at? Well, whenever I'm trying to find ans ij, I need ans ik, and I also need ans k plus 1j. But these are, again, substrings that are shorter than the original string, let's say. So it's very similar to the previous case. We have to sort these based on the lengths, based on j minus I, right? And if we sort them in that order, then whenever I want to find ans ij, I already have all of the answers that I need from the smaller subproblems. So I'm literally using the size of the subproblem, the number of matrices in my subproblem, as the ordering for how I'm going to compute these things. Okay, what is my runtime? Well, to compute the runtime, I'm just going to look at how many subproblems I have and how much time I'm spending on each subproblem. So first of all, I have n squared subproblems because I is between 1 and n and j is between I and n, so n squared, O n squared. But now, unlike the previous cases where I was spending only a constant time for each subproblem, here I'm actually spending O n time for each subproblem. Because for each subproblem, I'm basically considering all the cases. I'm saying which one of these multiplications is going to go last. And I can have up to n different multiplications, n different choices. So for each subproblem, I'm doing this for, which is taking O n time. So my total runtime here is actually O n cube. Okay. Again, this is because I had O n squared subproblems, each taking O n time. Okay. Which is not bad. So if I give you a chain of matrices and I tell you to multiply all of them together, I would expect that you first run this dynamic programming so that you know what's the best order for the multiplication. I mean, you're paying a cost of n cubed just to figure out the best order, but that would probably pay off. And then you can do the actual multiplication in the best possible order. Okay. I'm going to just give you more examples of dynamic programming. Here's another example. Let's say that as input, I give you just an array of integers. Okay. So I give you an array, let's call it A, of n integers. And I ask you to pick some of these integers. And I want you to maximize the sum, but I also want to tell you that you cannot pick two neighboring integers. Okay, so the output is this. What is the maximum possible sum of a subsequence that does not contain neighboring elements? Okay, and I can have negative or positive numbers. So let's say -0, 1, 1, 2, -1, something like this. So if I have this input, I can take, for example, 0 and 2, and that would give me a sum of 2, right? But I cannot take 1 and 2 because these two are neighbors. So I cannot get a sum of 3. Here I can get a sum of 2, but I cannot get a sum of 3. So in this case, the answer would. Okay. Now I want to solve this again using dynamic programming. Now, the kind of dynamic programming that I'm going to do here is actually very simple. So I'm just going to say, I define a subproblem, let's say ans I, and it's exactly what you think it is. I say, what is the maximum sum that I can get if I only have the first I elements? Okay, so the answer to the problem, if I only have the elements A1, A2 to AI. If I only have these, what is the maximum sum that I can find? But of course, I still have the requirement that I cannot take two neighbors. Okay. Now, here's the thing. Suppose I want to calculate ans I. Means that I have all of my elements and I have them until index I. So I can just do a casework. I either take the element at index I or I don't, right? So this is very similar to knapsack. If I take the element at index I, then I know that I cannot take the element at index I minus 1 because I cannot take neighbors. But then I can just take whatever subset of elements from index 1 to I minus 2 that I like. So if I take element I would get AI, and then for the rest, I have ans of I minus 2. If I don't take element I, well, I know that I'm not taking element I, so I can take any subset of the first I minus 1 elements as long as it satisfies the other requirements I had. So that's just the answer of I minus 1. And of course, I'm going to take the maximum of these two things because I want to maximize my totals. So that's it. And again, here the order of subproblems is very obvious. Just do it from left to right. Okay. And of course, I can say that ans 0 is 0. That's my base case. Okay. I actually need two base cases, right? Because it also depends on I minus 2. So I have to also say what is ans 1. So ans 1, you have to look at the first element. And if I only have the first element, what's the best that I can do? Well, if that element is negative, I'm not going to take it. But if it's positive, then I'm going to take it. So this is just going to say, is A1 positive? If it is, then take it. If not, then don't take it. So in C++ syntax, I can write it like that. Now, this is a very simple solution. Its runtime is, of course, ON, because I have n subproblems, and for each subproblem, I'm just calculating the resulting constant time. Okay. But this is a special case of something more general, and that more general thing is what we call prefix sums. So it happens very often that you have an array, and your dynamic programming is just to say, let's solve the problem on the first I elements. Whenever we have something like this, we usually say it's a prefix sum problem. Now, why do we say sum? Because people are used to summing all the elements. So that's the most common use case. But it doesn't have to be a sum. You can basically use whatever you want. So let's say my input is, again, an array with n elements. And let's say that I have to answer a bunch of queries. And every time a query just gives me two indices I and j. And as the output for this query, I have to write the sum of all the elements from index I to index j. Okay, so I have to write, let's say my array was A. I have to write AI plus 1 all the way to AJ. Okay. Now, a very simple way to do this would be that every time that you have a query, just start summing up and answer every query in ON. But we don't like to do that we like to just do one pre-processing of our input, maybe do some dynamic programming. And then ideally, I want to answer every query in constant time in O1. Now, this is again very simple. I can define my dynamic programming just like before. I can say ans ij is just the sum of all the elements from index I to index j, right? And then, well, I can also easily have a recurrence relation for this. I can say this is just ans of ij minus 1 plus the element at index j, right? But this is not good because I have too many subproblems here, right? For every pair ij, I have one subproblem. So I have n squared subproblems. My total runtime is becoming O(n) squared. Can I do better than that? Well, yes. Instead of doing all of this, instead of finding the sum for every substring of your array, just find the sum for every prefix, right? So just do this. Say that ans I is just A1 plus A2, so on to AI. So the sum of the first I elements of my array. Now I can easily compute this because I can just start from the beginning of my array, go forward and sum everything up, right? So if I want to write it as a dynamic programming, it's basically saying that ans I is ans I minus 1 plus AI. Pretty easy to compute all of these in linear time. But now someone gives me a query. When they give me a query, they want the sum of all the numbers in my array from index I to index j. So let's just visualize this. Let's say this is my array. And it goes from index 1 to index n. And someone has told me what is the sum from index I to index j. Okay. Now, of course, I have ans j, right? I can look at ans j. And what is ans j? It's the sum of everything from index 1 all the way to index j. But that's not the answer that I'm looking for, because it's also summing up these parts before I that I didn't like. So I have to subtract those. But what are those? Those are the sum of everything before I. So it's just ans of I minus 1. Right? So whenever someone asks a query and gives me I and j, I just do one subtraction. I take ans j, subtract ans I minus 1, and output that. So now I did a dynamic programming where I spent only linear time finding these sums. But when I want to answer the queries, I can do it in constant time. Now, again, this doesn't have to be a sum. So instead of summing up all of them, it could be, I don't know, XOR. It could be multiplication. You could do the same thing. But your operation should be reversible. So here, for example, when I'm doing sum, I have a subtraction operation, right? But if I were doing minimum, for example, there is no inverse for that operation, so I couldn't do something like this. We will see examples of how to handle minimum queries and so on later in this course. Okay, but I can also do these kinds of sums in more dimensions. So imagine that instead of having a one-dimensional array, I have a two-dimensional array or a matrix. Okay, so let's say my input is a matrix A. And I'm going to say this matrix is n by n, but it doesn't have to have the same dimensions. It's just, I don't want to have too many variables. Okay, so I have my matrix A and it's given to me in the input. I'm given all of the entries. Okay. And then just like before, I have a bunch of queries. But now every query just gives me a rectangle inside this matrix and says, what is the sum of all the elements in that rectangle? Okay. So the query is going to give me, let's say, x1, y1, x2, y2. And the answer to the query should be this. It should be the sum of every x from x1 to x2, the sum of every y from y1 to y2 of a xy. Okay, so every query is just giving me some submatrix, some rectangle, and is asking me what is the sum. Now, just like before, I can do this in the naive way. I can say whenever someone asks a query, I'm just going to do 2 for loops and sum them up and give the sum. But that would answer every query in n squared time. And that's too much for me. Again, let's imagine that I want to answer every query in constant time. Okay, so let's see what I can do. I'm going to draw this rather than actually write it because drawing is easier. So here's my rectangle, my main array, let's say, and suppose that this is what's being queried. So I want the sum of all the numbers in the red area. Now, one way is to look at every row and just do a prefix sum on every row, right? So I can say that for each one of my rows, I'm going to start from the beginning and I'm going to do a prefix sum. So if in this row I ask what is the sum from here to here, I already have it computed in my array, my dynamic program. Okay. So now, if I have a query like this, I can say just look at each row separately. So look at this row, for example, look at this row, then look at this row, and so on. And in each of these rows, I just want the sum from here to here, and this is just the previous problem, right? I can just find the sum from the beginning of the row to the end of this red rectangle, and then subtract the extra things that I have counted in it. Okay, so if I do this in my pre-processing, I'm going to basically calculate a prefix sum for each row. Now I'm saying each row, but I could also do it for each column. It doesn't really matter, it's symmetric, right? And then when I want to answer a query, I'm going to say go over each row and use the prefix sum. Now, this is going to be better than before, because before our query was just doing naively, going over every element in the red rectangle and summing it up. So my query was taking n squared time. Now my query is actually faster. My query is going to take only on, because every row of the red rectangle, its sum is calculated now in constant time. But maybe my red rectangle has n rows, right? So I have that problem. How about my pre-processing? How much time is my pre-processing taking? Well, I have to calculate a prefix sum for each row. Calculating a prefix sum took on, but I have to do it for n rows. So this is on squared. So this is fine. And honestly, I cannot make my pre-processing any faster than this, because, and here's a very common argument in this course, I have to read the input. And the size of my input is n squared. So just reading the input is going to take n squared time. And if I'm doing my pre-processing in n squared, no one can tell me do this faster. It's just impossible, right? But I want to do my queries faster. Can I somehow make the query faster? Well, yes, we can basically do something very similar. We can do a prefix sum, but we can do it in 2 dimensions. So this is 2-dimensional prefix sum. Now the idea is again very simple. Let's say I have this rectangle, which is my matrix. And I'm going to look at matrices that start at the bottom left. So I'm going to look at, for example, this matrix. I'm going to look at this matrix. They don't have to be square matrices. They can be of any size. I'm going to look at any matrix that starts at the bottom left. And I'm going to calculate the answer for these matrices. So I'm going to have a dp variable. Let me write it like this. dp of, let's call it AB, is going to be the sum of all the elements that are in the first A rows and the first B columns. Okay. Oh, by the way, I'm assuming that this is row number 0. If you're doing linear algebra, you might think that this is like row number 1. Doesn't matter. It works anyway. So I'm going to say dp of AB is the sum of all the elements that are in the first A rows and the first B columns. So sum of I from 1 to A and sum of j from 1 to B of Aij. That's what I want, but of course I don't want to calculate it like this, because if I calculate it naively, I'm going to actually spend n to the power of 4 time, right? So I want to calculate this dp in a better way. Now, how can I calculate it in a better way? So let's say I want this. I want dp of AB. So remember, this is the sum of all the elements in the first A rows and the first B columns. So let me just draw my thing again. This is my rectangle. And let's say this is the part where I want to find the answer for. So these are the first A rows and the first B columns. Okay. Here's what I'm going to do. I say, take this upper right element, just one element, and then I want to cover all the elements here. So I'm first going to sum up all these elements, everything here. This is hard to draw, so okay, let me do it like this, and let me do something like this. So I first sum up all of those elements, and that's, of course, dp of A and B minus 1, right? The first A rows and the first B minus 1 columns. Now I'm going to do something similar, but for the rest of them. So let's say I do it like this. I take these elements. Okay. This is dp of BA minus 1. Or dp of A minus 1B. Right? But now I have some elements that I have counted twice. Right? Any element that was here was counted twice. So I have to subtract them, but those are exactly the elements that are in the first A minus 1 columns and the first the first A minus 1 rows and the first B minus 1 columns. So I just subtract everything in here. So minus dp of A minus 1, B minus 1. And finally, I have this one element here that I have to add. So what is this one? This is just the element A of AB. So I just say plus A of AB. Now, you could define these rectangles in any different way. It doesn't really matter, as long as you make sure that you're counting every element exactly once. Right? Great. So now I have this recurrence relation, and I can use this recurrence relation to find all of these partial sums. I can find the sums for all of the rectangles that started at the bottom left. Right? And how much time does this take? Well, how many rectangles do I have? N squared. So A can be from 1 to N, and B can also be from 1 to N, so it's N squared. But for each one of them, I'm spending constant time. Right? So the overall runtime is N squared. And of course, you have to also remember how to handle the base cases. I'm not going to do that. Like the base cases, if you have no elements or if you have one element, you know what the sum is, right? So I'm not doing the base cases here, but this is taking O(n) squared. So now, again, my pre-processing is taking n squared, which is good, because I cannot do better than that. But now the question is, can I do a query any faster? So here's what happens in a query. In a query, I'm given a submatrix. So again, this is my main matrix. And let's say in my query, I have something like this. And I'm asked, what is the sum of all the numbers in the red area? Okay. And remember, this was like from x1, y1 to x2, y2. Right? That's how my query was given to me. Now, I'm not going to write this down algebraically because it's much easier to just show you geometrically how I'm going to answer a query. Basically, for any rectangle that starts at this bottom left triangle, sorry, bottom left point, I know the sum. So I have to somehow write this rectangle as a combination of rectangles that start at the bottom left corner. Okay, so not so hard. I'm just going to first take, this rectangle, right? So that's my first rectangle. Let's call it R1. And I'm going to just look at the sum in R1, okay? Now, this is counting a bunch of things that I don't like to count. So I have to subtract them out. Right now, I'm counting everything here, but I want to only count things in the red rectangle. So let's say I subtract this part. I subtract this part out. Okay. So let's call this one R2. So I say minus dp of R2. But I still have a problem because I'm counting these elements here. And I'm not happy with that. So I'm going to subtract them next. But I have to always start from the bottom left. So I subtract these ones. Okay. So it would be minus dp of this rectangle, R3. But now the problem is that if you look at this smaller rectangle, I added it once and then I subtracted it twice. But I should have subtracted it only once. So now I have to add it again. So I'm going to take this rectangle and add it again. Okay, so let's call this the fourth rectangle. This is dp of R4. Now, I didn't write it algebraically because it becomes a mess. But the point here is that any rectangle can be written as a combination of 4 of the rectangles for which we have pre-computed the sums. Right? So whenever I want to answer a query, I can just calculate this combination. And this is going to take O1 because I have these dp values for all of these rectangles saved from my pre-processing. So now finally, this means that every query is taking constant time, but my pre-processing was also taking n squared time. So my pre-processing is optimal and my query is also optimal. I cannot do better than this. Now you can imagine that I can also extend this to 3 dimensions, 4 dimensions, and so on. It's just that this part gets a little bit more complicated. You have to do the inclusion-exclusion principle. Okay, let's see. Let's do something else now. Another type of dynamic programming that we're going to see very often is dynamic programming on trees. And this is why we had a lecture on trees yesterday. So suppose I give you a tree and imagine that one of the vertices is chosen as the root, because generally if I just give you a tree, there is no particular root vertex, but let's say you arbitrarily chose one of the vertices as the root, okay? So let's say my input is a rooted tree. So for example, I can have a tree like this. It has a bunch of vertices, vertex 1, 2, 3, maybe, I don't know, 4, 5, 6, and like 7, something like this. Okay. Now, one of the things that we have used very often in our algorithms before was the concept of height and also the concept of depth, right? So I'm going to define a height for every node, and I'm also going to define a depth. So I'm going to say the height of a vertex U is basically the distance from U to its lowest possible descendant. So if I start at U, how many steps can I take going down? Okay, so distance from U to its farthest descendant. This is how I'm going to define height. And I'm also going to define a depth, or sometimes we call it a level. And I'm going to say depth of U is the distance from U to the root. So how many steps can I take if I always go up? Okay. Distance from U to the root. And what I want you to do in this problem is that just in the output, write all the heights and depths. Okay. So print all heights and depths for all vertices. Now, when we were doing DFS, we already did this kind of thing, and I've already coded it for you. I just want you to see that this is a special case of dynamic programming, right? Because what's happening here? Let's do height first. The height of a vertex is the distance from that vertex to its farthest descendant. So it's like I start here, how many steps can I take going down? Okay, so let's just do the example here. Let's do height. It's very intuitive, right? I can start at the bottom of my tree, and I can say the height of the leaves are 0. So basically this leaf has a height of 0, this one has a height of 0, this one has a height of 0. And then at this node, I say that it has a child with a height of 0, so its own height is 1. Here, it has a child with a height of 1 and a child with a height of 0, so its own height is 2. And so on. So this one has a height of 1, this one has a height of 3. So what I'm actually doing is a bottom-up dynamic programming. I'm doing dynamic programming, but I'm starting at the bottom of my tree. So this is what I'm saying. I'm saying if some vertex U is a leaf, if it doesn't have any children, then the height of U is 0. Otherwise, the height of U is going to be 1 plus the maximum height among its children, right? Plus the max over every V that is, let's say, a child of U of height of V. This is the recurrence relation that I have. So I can do dynamic programming. Again, these are my subproblems. So you see that if I just order them from the bottom of the tree up, I have the correct ordering. So I can calculate these height values by starting at the bottom of my tree and just going up and using these formulas. Okay. Now, the case of depths is the exact opposite. I have to start at the top of my tree and go down. So these are generally the two types of dynamic programming on trees that you will see. You have top-down dynamic programming and you have bottom-up. So suppose I want to do depths. Let me just copy this again. So if I want to do depth, remember the depth was basically the distance to the root. So the root itself has a distance of 0 to the root. And then its children have a distance of 1 to the root. And then this one, in order to go to the root, it has to go to its parent. But the parent has a distance of 1, so this one is going to have a distance of 2 to the root. Similarly, this one has a distance of 2, this one has a distance of 2. And 7, again, if I start from 7, I want to get to the root, I have to first go to the parent of 7. But I know that from the parent of 7, it takes 2 steps to get to the root. So from 7, it's going to take 3 steps to get to the root. Okay? So my recurrence relation is like this. I'm going to say if u is the root, then depth of u is 0. Otherwise, the depth of u is just 1 plus the depth of the parent of u. Okay? So now, again, if you look at this as dynamic programming, I have subproblems. I have a subproblem for each one of my vertices. And when I'm finding the answer for u, I need to already know the answer for the parent of u. So I have to order my vertices from the top of the tree down. So if I want to calculate all the depths, I'm going to start at the top of my tree and I'm going to go down and just use this formula. Now, how much time do these things take? Well, this one is pretty easy, right? At every vertex, I'm spending constant time. So this is definitely ON, right? This one is a bit trickier to work with. So if I'm at a leaf, I'm spending constant time. But if I'm at a vertex that is not a leaf, I'm going over all of its children and I'm calculating this maximum. So the amount of time that I'm going to spend at this vertex u is going to be the number of children of u, right? So what is my total runtime? My total runtime is, well, at every leaf, I'm spending O1 time, right? So O1 times number of leaves. But at every other node, the amount of time that I'm spending is basically the number of children of that node, plus the sum over every vertex u that is not a leaf, of the number of children of u. Okay? But what is the sum of the number of children of all the nodes? It's at most n, right? Because every node is only counted among the children of its parent. So in this sum, I'm counting each one of the nodes at most once. So this whole sum is ON. And of course, this part is ON because I have at most n leaves. So the whole thing is ON. Okay. Another way of looking at this is to imagine it like this. Imagine that each one of these nodes is going to somehow send its height value to its parent. And we want to see how many messages we're sending from children to parents, right? Now, each child sends exactly one message to its parent. So the total number of messages is n. Now, of course, each parent can receive messages from all of its children. If it has many children, it's going to receive many messages. But that doesn't affect the total number of messages. Each person, each child is sending one message up. So the total runtime is ON. Okay. So let's take this previous problem that we had. Let me see which one. Yeah, let's take this one. And let's extend it to trees. So remember here, I had an array of numbers. I said I want to take a bunch of these numbers, but I cannot take neighbors. But they were in a line, they were an array. Now let's say I have a tree. So this is now the problem I want to consider. My input is a tree. But each one of the vertices in this tree has a value, okay? So there is a value assigned to every vertex. So imagine that I have a function called val, which takes my vertices and assigns a real value. Now in the output, I want to say I want to take some of my vertices so that I maximize the total value, but I cannot take any two neighboring vertices. So if I take a vertex, I cannot take its parent, and I cannot take any of its children. Okay? In the language of graph theory, this is finding an independent set. So I want to find an independent set with maximum total value. So maximum total value of an independent set. Of course, if all of my vertices have value of 1, this is just going to give me the biggest independent set, the size of the largest independent set. And as usual, I'm really obsessed about the value. I'm not obsessed about the actual solution because I can trace my steps back and I can find my actual solution. Okay, so let me again copy my tree. Now, remember that in my input, I just said I have a tree. I didn't say that this tree has a particular root. But you can always just choose one of the vertices as root yourself, right? And then you can just do a DFS from that vertex, figure out who's the child, who's the parent, and so on. So I can just assume that I have a root. That's my first step. Choose a root. And in this case, I'm just going to choose vertex 1 as my root. Okay. Now, here's what I'm going to do. I'm going to say for every vertex, I want to define a subproblem. Now, what is a natural way to define subproblems? Well, I can take a vertex and everything that comes below it, all of its descendants, and I can say this is the subtree corresponding to this vertex. And I can define a subproblem on this subtree. Okay. So in this case, let's say that, well, let me first give the values. So let's say this one has a value of 2, this one has a value of -1, this one has a value of 5, this one has a value of 0. Let's say this is value 6, this is value 2, this is value 1. Whatever. I just gave some values to all of the nodes because this was needed in my input. And now here's how I'm going to define my dynamic programming. I'm going to say for every vertex u, ans u is going to be the answer to my problem if I only had vertex u, its children, its grandchildren, and so on, everything that comes below vertex u. So it's the answer of the same problem on the subtree of u. And by this, I mean u and its descendants. Okay. So for example, ans of 2 would only look at this subtree, right? Ans of 5 would only look at 5 because it's its own subtree. Ans of 3 would contain these vertices. And of course, ans of 1 will contain all of my graph. Ans of 1 is the entire tree. And so if I can somehow find these answers, then my final answer is just the answer at the root. And I can output that. Okay. So now I want to find recurrence relations. Well, first of all, let's decide. Is it easier if I start at the top of my tree and go down? Or is it easier if I start at the bottom and go up? It seems easier if I start at the bottom, because the way I'm defining my subproblems, as I'm going up, they're becoming bigger and bigger. So I don't want to start with my biggest subproblem. Intuitively, I want to start with the smallest one, right? So the first thing is, what is the answer at vertex u if that vertex is a leaf. So if u is a leaf, what can I say about the answer at u? So u is a leaf. For example, vertex 7 here is a leaf. So when I'm calculating the answer at 7, I'm only looking at 7 itself. There are no children, right? So I have two choices. Either I pick 7 or I don't. Of course, if it has positive value, I'm going to take it. If it has negative value, I'm not going to take it. And let's create a leaf here with negative value. So let's say 4 has value -1. So ans of 7 would be 1, but ans of 4 would be 0 because I don't take the negative value. Okay, let's actually let me give it some other value now, 3, whatever. So if u is a leaf, the answer at u is to just look at the value of u. And if the value of u is positive, I'm going to take it. Otherwise, I'm going to take 0. So I can just say this is the maximum of the value of u and 0. That's what I'm doing at a leaf. But now, let's say that I'm looking at a non-leaf node. So this was 7. Let's give this cost of 2. Let's give this one, I don't know, a cost of, or a value of 10 now. Okay. Let's say I'm looking at a node here. For example, I'm looking at node 3. And this is the subtree. I want to figure out what is the best independent set that I can take in this subtree. Now, again, just like before, I can say, let's look at the root. And I have two choices. Either I'm taking the root in my solution or I'm not taking the root. Okay. So otherwise, if u is not a leaf, I say my answer is the maximum of two cases. The case where I took the root into my answer and the case where I didn't. Right? So let's see. If I take my root, if I take 3 in my answer, what does that mean? It means that I cannot take any of its children. Right? So I've picked 3 because I cannot take any of its neighbors. I cannot take 5 and 6. But then from the grandchildren, if I have a bunch of grandchildren, I can take whatever I want. Right? So in this case, my answer is just the value of the root plus the sum of the answers at all of the grandchildren of the root. Okay. So I call this case 1, and I say that case 1 is the value of the vertex u plus the sum of the answers at all vertices g, such that g is a grandchild of u. Okay, this is my first case. Now, my second case is that I'm not taking the vertex u, the vertex v itself into my answer. So if I'm not taking that, then from each of the subtrees of its children, I can just pick the best possible answer. Right? So I can take the children if I want to. I can take whatever I want from the subtree of this child, whatever I want from the subtree of this child, and so on. So in the second case, so remember my first case was the case where u is taken. And my second case, C2, is the case where u is not taken. In this case, because I don't take u, I don't have to add the value of u, but then I go over all of the children of u, and I sum the answers for them, where v is a child of u. Now, of course, in the end, I want to find the solution with the maximum value, so I'm just going to take the maximum. So at the end, I'm just going to say that the answer at u is the maximum of these two cases, maximum of C1 and C2. That's the recurrence relation that I have. And now, this is very similar to the previous cases, except that I have grandchildren involved here as well. But in any case, whenever I'm calculating the answer at a particular node U, I only need to know the answers at the descendants of U, at its children and grandchildren. So I could just start from the bottom of my tree and keep going up and calculate all of these answers. Okay. What is my runtime? You see, one way of looking at this is that every vertex can have a ton of grandchildren. It's possible that every vertex has almost n grandchildren. So I can say that this sum is going over at most n different values. And of course, I'm doing this for every one of my vertices, so it's n squared, O(n) squared. That's a valid analysis, but it's not tight. I can do better than that. And the way I can do better is by figuring out that even though any node can have many grandchildren, any grandchild can have only one grandparent, right? So when I'm calculating these sums over the grandchildren, I'm summing up the value of every node at most once, because every node has exactly one grandparent and it only contributes to the sum in its grandparent. And here I can say the same thing. In this sum, every node has exactly one parent, and it's only contributing to the sum at its parent. So the total runtime here is actually still O(n). This is a linear time algorithm, where n is the number of vertices. Now, I can present the same algorithm in a slightly different way. So imagine that instead of doing these things, instead of saying that my values can depend on the values at the grandchildren, I wanted my values to only depend at the values in the children. I could define my values, but it would become a little bit more complicated, but it's basically the same idea. So this is an alternative way of doing the same dynamic programming. Here's what I'm going to do. Before, I had just one value calculated at each one of my nodes. Now I'm going to calculate two different values at each one of my nodes. So I'm going to do this. I'm going to say I have ans 0 of U and I have ans 1 of U. And ans 0 of U is basically the maximum value of an independent set in the subtree of U. Okay, except that I want to make sure that I don't take U itself. Okay, so I only look at the independent sets that are excluding U. So I can take any of the descendants of U, but I cannot take U itself. With that constraint, what is the maximum value that I can extract? And similarly, ans 1 of U is going to be the maximum value including U. So if I look at all the independent sets that definitely have U in them, I am forced to take U. What is the maximum value that I can take? So this 0 and 1 here is basically 0 saying U is not there, 1 is saying U is in there, right? Now, of course, you can see the connection between these values and the values I had before, right? Because before I said that the ans at U is just the maximum value of an independent set in this subtree. So any independent set in this subtree is either going to include U or not include U, right? So ans of U is just the maximum of ans 0 of U and ans 1 of U, right? So if I could just calculate ans 0 and ans 1, then I could also find the value of ans that I had in the previous solution. Now, this is kind of easier to do now. right? So let's say I want to do ans 0 of u. What does this mean? This means that I have the vertex u, and I'm looking at its subtree, everything that comes below u. But I know that I'm not taking u itself into my solution. Okay? Because I'm not taking u into the solution, from any of its children, I can basically decide what to do. So let's say these children are v1, v2, so on. At v1, I can say I take v1 into my solution or I don't. At v2, I can do the same thing. And by the way, the choices that I make for the subtree of v1 are completely independent of the choices that I make at v2, v3, and so on. Because these subtrees are not even connected to each other. They're only connected to each other using u. But I know what I'm doing with u. I know that it's a 0, so I'm not putting u into my solution. Right? So ans 0 of u is just going to be the sum over all v that is a child of u of ans of v. Now I'm using ans, but I could also write max of ans 0 and ans 1, right? Great. Now what is ans 1 of u? Ans 1 of u means that I have this subtree rooted at u, and I'm taking u itself into my solution. So that's already giving me the value of u. But then from each of the subtrees of its children, for example, from the subtree of v1, because I have taken u, I know that I cannot take v1 itself. So from the subtree of v1, I'm going to take the best solution that does not include v1. And then I'm going to do the same thing for v2 and so on. So this is again plus the sum over all v that is a child of u of ans 0 of v. Okay? And that's it. Now I have two values, ans 0 and ans 1, at each one of my vertices. But I can still compute them in a bottom-up fashion, right? So if I know the ans 0 and ans 1 of the children, I can find the ans 0 and ans 1 of the parent, right? And of course, you can see that the intuition here is pretty much the same as the intuition before, right? So this is also ON, because when I'm doing ans 0 of u, I'm going over all children of u. And again, each vertex is a child of only one other vertex. So this sum goes over each v exactly once in my entire algorithm. And here, it's again the same thing. So it's ON overall. Now, do whichever you like. If you like, you can implement it with the grandchildren. If you don't like, you can have like one extra bit of information here. And it's pretty much the same algorithm. Okay. Let me see. Let me just do one more. Let me do diameter. So this is the diameter problem. Let's say in the input, I give you a tree with vertex set v and edge set e. And in the output, I want you to write the diameter of this tree. So the maximum distance between any two vertices. Okay. My output is the diameter of t, which is basically the maximum over all vertices uv of the distance from u to v. And I'm assuming that all of my edges have weight 1. So the distance is just the number of edges. So what is the maximum distance? And again, as before, I could also ask you to output the two vertices that have the maximum distance. Now, there are many ways to solve this. You can actually solve it using DFS too, but I'm going to solve it using dynamic programming. And I'm going to use what we calculated here. We calculated heights and depths, right? So let's use the height version, for example. So let's say that in the first step, I calculate all heights. I know how to do this. For every vertex, I know how to calculate its height. This is basically what I did here. So let me just copy this. Okay, this is my graph. Oh, and by the way, I always have this first step and I forgot it. So this is not step 1. This is actually my step 2. My step 1 is choose a root, right? And I can choose my root again as I like. Choose whichever vertex you want as the root. Usually when I'm coding these things, I always choose vertex 1 as the root. That's the easiest and laziest choice. But anyway, it doesn't really matter. You can choose whichever vertex you want as the root so that we can talk about parents and children and so on in our DP. Okay. And so I've chosen vertex 1 as the root. I have calculated all the heights. And now I want to find the diameter. So here's the thing. Let's do something similar to before. Let's say d of u is the diameter of the subtree rooted at u. So I'm going to take u and all of its descendants, and I'm going to say, suppose I only have these vertices. What is the diameter here? Okay. Now, for example, let's say my vertex u is 1. I want to see what is the diameter of everything in this tree. I have 2 vertices that have the maximum distance among them, right? Now, here's the thing. 1 has 2 children. I have the subtree of the left child, and I have the subtree of the right child. Now, in general, I might have more children. It's not a binary tree, okay? But here's the thing. The 2 vertices that are farthest away from each other, they're either going to be both in the same subtree, so in the subtree of 2 or the subtree of 3, or they're going to be in different subtrees, okay? This is the casework that I'm doing. If they are both at the same subtree, well, I already know the answer. I can just look at the answer there. So I can say d of u is, well, I'm going to take the maximum of d of v for every v that is a child of u. Okay, v is a child. Okay, so this covers the cases where the 2 vertices that are farthest apart from each other were in the same subtree, in the subtree of the same child, right? But maybe, for example, suppose this is the farthest path. Maybe they're in 2 different subtrees. But if they're in 2 different subtrees, each of them is going to be a leaf, and each of them is going to be as far from the root as possible, right? So if I'm going to take someone from this subtree, for example, it's going to be this leaf 4. If I'm going to take someone from this right subtree, it's definitely going to be 7, because that's the one that is farthest away from the root. And I have to start somewhere, go to the root, go to a different subtree, and keep going, right? So in this case, what is the distance? Well, the distance is basically the distance from the root to the farthest point in this subtree plus the distance from the root to the farthest point in this subtree, right? But that's just the height of this child plus 1 plus the height of this child plus 1, right? Now, in this case, I had only 2 children. If I had more children, I could choose which one I want to take. But I want to have the longest possible path. So I'm going to take the 2 children that have maximum heights. Okay? So I'm going to say, let V1 and V2 be the children of U with maximum height. The children of U with largest heights, largest possible heights. So I'm going to say that I can start from U and I can go to V1 and then go down by the height of V1. So that would give me 1 plus the height of V1. I can also start at U, go to V2, and then go down by the height of V2. So that gives me 1 plus height of V2. So overall, it's 2 plus height of V1 plus height of V2. Okay. So this is the longest path that goes between two vertices in two different subtrees, in subtrees of two different children of U. And this was the length of the longest path in the same subtree. I want the length of the longest path overall, so I'm just going to take the maximum of this and this, right? And that's going to give me the longest path overall. Okay. Now, what is my runtime here? Here's the thing. At every vertex U, I'm looking at all of its children. So this part, if I only had this part, if I didn't have this one, would be ON, just like before, because I say that every child is only seen in its parent. But how much time do I need here? It's not actually O1, because I have to go over all the children, and I have to find the children that have the biggest heights, right? But again, I can just walk over the array of children and I can look at the heights, and I can always remember not only the highest height, but also the second highest height, right? So that's also going to take a time which is like, oh, the number of children of this node, right? So again, overall, the runtime is ON. But of course, I had to also calculate the heights. Calculating the heights was also ON. So the whole thing is ON. So total runtime, ON. And I'll see you next week.